The inherent efficiency of steel wheels rolling on steel rails has the consequence of very long stopping distance. At normal operating speed, stopping distance is much greater than sight distance. Operating a train is like driving a car in almost zero visibility weather conditions on an ice-covered road. The engineer's sight distance must be extended artificially for a train to operate safely at commercially viable speed. The engineer must know that the track ahead is clear for the distance required to stop at the current speed. Where the speed allowed on the track varies, such as it switches, the engineer must know in advance what the maximum speed at that location will be. Historically, there have been a wide variety of railroad signal types in North America. The semaphore is the only one of the early signal types to remain in use into the 21st century. The principle is simple. Horizontal means stop. 45 degrees upward means that some cautionary action is required, and 90 degrees upward means the track is clear. Some systems only had two positions, horizontal for stop and diagonal downward for proceed. The semaphore is constructed with red, yellow, and green glass lenses. A light is mounted in a way that illuminates the red lens at horizontal, the yellow lens at 45 degrees upward, and the green lens at 90 degrees upward. Originally, the light was a kerosene lamp. Later, semaphores were equipped with electric lights. As electric light technology improved, signal systems were developed that conveyed information using only colored lights. The color position light and the position light signals use a combination of lights and an angle of the combination of lights that emulates the position of a semaphore. These signal types introduce two levels of redundancy for safety. These signal types have a high degree of visibility because of the multiple lights to convey information that is conveyed by only one light on a semaphore. The position light had only yellow lights as yet another safety feature. The color of the lights was specifically selected for the best visibility in fog. The searchlight signal was developed as a means of conveying the information by use of a single very bright light. The color is changed by a moving element inside the signal housing that has three colored lenses, much as on a semaphore. The most widely used signal type is the color light signal. It is a housing containing three light bulbs and three lenses. Position light and color position light signals use two or three light bulbs to produce the same information as one bulb of a color light signal. Semaphores and searchlight signals have moving parts. These four signal types are gradually being replaced with color light signals. The configuration of the signals as well as the color of the lights convey information. A single signal may consist of several individual signal units containing lights and colored lenses. The signal units may be mounted on a mast or directly to a concrete foundation, a configuration known as a dwarf signal. The meaning of the lights may also be supplemented by a number plate, generally the milepost location of the signal, and or by off-center mounting of the signal units. A signal may be located to the left or the right of the track it governs, as long as which track it governs is clear when it is observed. If the signal cannot be located to the left or the right of the track and be clear in which track it governs, it may be mounted on a bridge constructed for the purpose or on a cantilever, which is a similar bridge supported on only one side. Collision prevention was the original purpose of signals. The track was divided into sections called blocks. Originally, each signal conveyed only the information of the block it governed, occupied or clear. The signals were manually operated by employees and stations. The condition of the block was conveyed between the stations at opposite ends of the block by telegraph or telephone. The signals governing entry to a block are called block signals. The development of a way to automatically control signals by using electric current in the rails to detect the presence of a train allowed lengthening the view to the second, third, or fourth block ahead, allowing even greater speed than the occupied or clear arrangement allowed. Instead of the train approaching every signal prepared to stop, the signal would present information far enough in advance to allow the train to operate at normal speed past every signal that indicated that the line was clear. Block signals are located at intervals that allow a train moving at the speed limit to stop at the next signal. However, the blocks are typically located at an interval that allows stopping from less than the speed limit, depending upon the signals before the stop signal to convey information that shows the train as it approaches the stop signal. Break. Block signals are located at intervals that allow a train moving at the speed limit to stop at the next signal. However, the blocks are typically located at an interval that allows stopping from less than the speed limit, depending upon the signals before a stop signal to convey information that slows the train as it approaches the stop signal. Signals are used for traffic control as well as collision prevention. Originally, if a train needed to change route, the train had to stop to allow a crew member to get off and change position of the switch manually. The development of systems to control several switches from a central location facilitated train movement. An employee dedicated to that purpose could align the switches for the route of each train as it approached. Signals began to perform the function of traffic signals at these locations, informing the engineer of an approaching train if a stop was required, generally for conflicting traffic, or if the train could proceed through the switches. The signals and switches are connected in a way that prevents signals from authorizing conflicting movements in the controlled area and prevents the alignment of switches from being changed under or right in front of a train after the signal has authorized it to proceed. The arrangement of switches and signals that protect an authorized movement over them is called interlocking. The interlocking limit is the extent of the controlled area. Entry to the track within the interlocking limit is controlled by a signal called a home signal. Each track entering the interlocking has a home signal. The home signals convey to the train engineer the route through the interlocking and/or the speed limit through the switches in the interlocking. Home signals are almost always automatic block signals as well. Control of the signal by the employee operating them consists of stop and not stop. When the signal is set for not stop, it becomes an automatic block signal, conveying not only the route and/or speed through the interlocking, but also the block signal information for the track beyond the interlocking. Interlocking technology originally allowed an employee to control the switches and signals at one station within an area of a few hundred feet. Some large stations require 2 or more interlocking stations. As electric and electronic technology developed, the area that could be controlled from a single interlocking station increased from hundreds of feet to thousands of feet. Ultimately, electronics allowed one interlocking station to control the interlockings at many stations. This development, generally called CTC, allows the train dispatcher to manage the flow of traffic and the maintenance activities on the track over a length of many hundred miles.